Hi, my name is Hussein Sharafuddin. In this video, I'm going to demonstrate to you this project that I made for my thesis in order to feedback control permanent magnet AC motors. This is a microcontroller based device that performs the controlling of the motors. I use the Arduino Duo since it has powerful performance and functions such as the built-in decoder to measure the position of the motor. Here's the hardware setup. This is a DC power supply, which is connected through these capacitors to the converter. This converter converts the DC voltage to three-phase AC voltage. Notice that the converter is controlled by the microcontroller, in this case by this device. Basically, this converter is built with three half bridges. Each one consists of two IGBT transistors. This device measures two currents of the motor and sends the corresponding voltages to the microcontroller. This is a permanent magnet AC motor, and here it has a rotary encoder so that the position of the magnets inside the motor can be calculated. The encoder is also connected to the microcontroller. I built various functions in the software of this device, but I will show you the interesting part of it. The technique that I use to control the motor, it's not the field-oriented control. I use the direct self-control instead. This technique was presented by Dippenbrock around 1985. This technique of motor controlling is usually used where the heat loss of the conversion is required to be as minimal as possible. I might make a video in which I explain the direct self-control. I also tried to make an optimization to this technique so that the harmonics in the waveform of the current are reduced. Now I can navigate to the desired function and I can start it. Notice that the menu is written in German. Now I can, with this rotary encoder, set the desired speed of the motor. This is the desired speed and this is the actual speed of the motor. As you can see, it is working very good and the response is very good. Now I will switch to the optimized version. And this one is also working very nice. In order to compare both versions of controlling, I wrote a PC software in Python that receives the data from the microcontroller through this USB connection so that we can plot all the signals that we want to observe. So let's have a look at it. So this is the hardware setup again. This is the device that I developed and it's connected with the PC with a USB cable. This is the converter that converts the DC power into three-phase AC voltage. And we have here the device that measures two current values and send them back to the microcontroller. Notice that we need only to measure two currents because we can calculate the third one from there. And here we have the rotary encoder signals, which also are connected with the device, so that we know in which position the rotor is. This is the software that I wrote in Python to control and to plot the signals of the motor from here. And if I start the direct self-control from here now, you should see the motor calibrated now, and I can set the desired speed from here and start controlling the motor from the software, as you can see down. And now I can see the signals of the motor in real time. And now you can see the overshoot there. I can change the speed as I want. This is a very good moment to show you the flux vector in the machine, and you see that the flux has this hexagonal form, and this is the main character of the direct self-control. The direct self-control uses three hysteresis controllers to control the flux in this waveform. I think I will talk about this in another video. But there's a disadvantage. If we have a look at a phase current like this, we see that this phase current does not have a sine wave. And if we look at the fast Fourier transformation of this signal, so that we see the harmonics in this signal, we see here that we have, this is our 3 Hz, and we have a lot of harmonics there. So that's why I try to make this optimization to change the to reduce these harmonics. And if I start now the optimized version of the direct self-control, and I'll set the speed and plot it again, and you can see now we have all the signals, we can observe them live. And now if we have a look at the flux vector, you see now that the flux vector has this circular form, and it hasn't the hexagonal form anymore. And that is good because if you have a look at the current of one phase, for example, you see that it has more sine wave than the other one. And if we look at the fast Fourier transformation of this signal, we can see that there is much less harmonics in the signals, and that's why it's better. The only thing here that we have a little bit more switching. I also implemented a position control. I used the speed control loop as an inside closed loop, and I made another loop to control the position of the motor. This gives us a cascade control. And you see here, if I choose a desired position, the motor follows. I can play a little bit with it here, and you say that you see that it's following. These are the main functions of this project. I think I will make another videos or a series of videos in which I go in details about these whole functions and things, and maybe a little bit about the theoretical background of this project. Thank you very much for watching, and I'll see you next time.